Hello everyone, I'm MC. I'm a PhD student at the mplab at INSA de Lyon, and this video is a part of a series about rapid control prototyping for electrical motors. So the goal of these videos is to show that the use of MATLAB, Simulink and mplab device block for Simulink facilitates the implementation of real-time advanced control strategies for electrical motors, and hopefully to share with you also the codes we're developing here at the mplab. And here I'm going to specially focus on field weakening of PMSMs. And at the end of the video there will be an experimental demonstration of the algorithm. So I recommend also to see the video on vector control, as field weakening is just an extension of that work. So the field weakening algorithm we're going to present here is a joint work with my supervisors, Federico Bribiesca, Paolo Massioni and Romain Delpoux. So I'm going to start by a small introduction on PMSMs. So surface-mounted permanent magnet synchronous motors are widely used in the industry, for example in automotive applications, in robotics or in power generation. And the goal is to produce torque while minimizing the current, and this despite of the limitations of the system, the physical limitations of the system. So to give an intuitive grasp of the field weakening problem, I'm going to use this schematic, simplified schematic of a three-phase PMSM. So when the rotor spins, it induces a back EMF voltage, which is the opposite of the voltage we're applying to the system, and this leads to an available voltage that is smaller at high speed, a little bit smaller. That is smaller at high speed. So something like this. And this what actually causes the voltage limitation of the field in the field weakening problem. So we can see that in the model of the SPMSM. This is the back EMF term in the model. So when the speed increases, you see that the available voltage to control the system is smaller. And the idea here, the trick, is to add a negative ID current to be able to reduce the effect of this back EMF term and still be able to drive and control the system at high speeds. So this system is mainly subject to two constraints, which are the current constraint and the voltage constraint, written in the following ways. And this current constraint is mainly dependent on the cooling capacity of the system, whereas the voltage constraint depends on the rated voltage of the inverter and the type of the modulation we are using. Which means, are you using space vector modulation, sinusoidal modulation, or other? The voltage saturation can be drawn in the VDVQ frame, and it's a circle of center 0 and of radius V max. And the current constraint can be drawn in the IDIQ frame, which is a circle of center 0 and of radius I max. So what we're going to try to do is to write this voltage saturation in the IDIQ frame. So to do so, we're going to use the equations of the system. So basically we take the current equations but in the steady state, and you can see that here we can write VD as a function of this and VQ as a function of this, and then we can rewrite this constraint into the IDIQ frame. When we do so, we have the following equations. So here you have the current constraint, and here you have the voltage constraint, which is now a circle in the IDIQ frame, and the circle has a center that depends on omega and the radius that depends on omega. So when the speed is going to increase, the radius radius of the circle is going to shrink, and the center is going to move around in the IDIQ space. And the more the speed increases, the more you can see here that the voltage limitation is going to be stronger and needs to be dealt with in order to be able to drive the motor at high speeds. So this problem can be written as following. So we want to minimize the IDIQ currents in steady state, taking into consideration the current saturation, the voltage saturation, and the torque constraint. So our block, the implementation is going to look something like this. So we have the field weakening algorithm, which basically solves this problem and take as an input the torque, the load torque, and the speed we want to operate at, the maximum voltage available, the maximum current available, and is going to give you the optimal IDIQ to implement on your system. So now we can rewrite this problem in a following way. So we can represent this problem in a more graphical way in the IDIQ frame. You see here in green is the current saturation, the current limitation. In red is the voltage limitation at a given speed omega, and in blue is the load torque. So you can see here that the optimal point can be found easily, which is this one, and the algorithm actually is going to compute this point. So you see if the torque increases, for example here, the solution is going to be here. And of course, if this voltage saturation moves, we get at higher speeds, the optimal point is going to be found accordingly. And one other interesting thing to note is that the maximum torque at a given high speed is this one. And we can use this information to better handle our controller. So, after presenting the problem, I'll be giving the Karosh-Kuntuker optimality condition, which is hopefully just a framework in which we can solve this problem, and finally experimental validation. So the Karosh-Kuntuker optimality conditions is basically solving for these 4 cases when no saturation is active, so we don't need any field weakening, when the voltage saturation is active, when the current saturation is active, and when both voltage and current saturations are active. We can also, when the problem is not feasible, we can try to find a feasible point that is near to the unfeasible point we asked the algorithm to solve for. But this is not detailed here. You can see the paper for more details, which I will leave a link in the description for. So, the experimental validation. So the control strategy implemented is the following. So here we have the synchronous machine, and the part that is implemented on the embedded controller is this one. This is just a field-oriented control, the classical one, with an electrical controller and the mechanical controller. And here we're going to add this field weakening block, which takes as an input the speed, the IQ, which is just an image of the torque, the maximum voltage, and the maximum current available. And it's going to compute accordingly the IDIQ current to be applied to the system. And of course, the maximum torque available at a very high speed is going to be used as a current saturation limit to be able to build an anti-wind-up for the mechanical controller, to avoid the very high, to avoid the integrator problems. So this is what we're going to implement on the microcontroller, and that's what we'll see next. So after uploading the code into the microcontroller, I will use the PIGGY, which is basically a tool that allows you to plot your measurements in real time. Here you can see the voltages applied to the motor in the VD, VD and VQ. And you can see the currents IDIQ and the references generated by the flux weakening program. And here you can see the speed omega and the reference speed asked by the user. And in the IDIQ frame, you're going to see the different limitations of the system, and especially current limitation and voltage limitation, and of course the operating point computed by the flux weakening program. So in order to run the experiment, first I'll be pressing the on button, which allows me to do a test into the open loop mode. If I press the second button, I'll be in the speed control with the flux weakening option, of course. If I increase the speed, maybe to a little bit more than 2000 RPM, you can see that the voltage limitation is starting to appear into the ID-IQ frame. Of course, the ID, no ID current is necessary to reach this speed. We can increase a little bit more. A little bit, 4000 RPM. You can see now that the ID current is somewhere around -4 amps. Now a little bit more than -5 amps. And of course the measurements now are beginning to be very noisy because there's a lot of vibrations on the motor. I'm going to decrease the speed. As you can see, the flux weakening program is going to adapt. So this is it for the experiment. If you want, we have the code available here on the website that we're going to leave a link for in the description. Here you can see there is the field weakening program with a lot of explanations, and of course you have the algorithm over here and the references at the end of the page. And of course, if you're looking for the code, you can find it by clicking here or going to the Git from this place, and of course from this button. And of course you can also check our other YouTube videos on this subject of rapid control prototyping. Thank you for your attention.